In the last lecture, we finished our study of Greek mathematics, and in this lecture we move on to Indian mathematics. The origins of Indian mathematics are rather uncertain. The earliest records that we have actually come to us from the Vedas, the great epic poems that were written in the mid to late second millennium BC. The mathematics that's contained in the Vedas is very sketchy, and often what is found there is more of a mnemonic device, and so it's open to a great deal of interpretation what exactly is being described in the Vedas. But there is a collection of works that really are appendices to the Vedas, what are known as the Sulba Sutras, written in the period roughly 800 BC to 200 BC. And these describe how rituals were to be performed, and they lay out the way in which altars were to be constructed, things such as this. And so there's a fair amount of mathematics that's contained in the Sulba Sutras. And so one of the problems that the Indian priests would face is one of, say, doubling the area of an altar. And in order to double the area, what you need to do is take the length and the width and multiply each of those by the square root of 2. So the Sulba Sutras explain how to find a good approximation to the square root of 2. They also explain how to compute volumes. If you want to double the volume of a given altar, you need to multiply each of the 3 dimensions by the cube root of 2. And so these also explain how to find good approximations to the cube root of 2. We do find references to the Pythagorean theorem here. We also find references to interesting counting problems, because one of the ways in which the Vedas and the Sulba Sutras and these other poetic forms was memorized was to recombine the syllables. And people were often interested in the number of ways that these could be recombined. And some of our earliest work on what we call combinatorics actually comes from these kinds of investigations. The earliest recorded writing that we have of Indian mathematics also makes it clear that they were using a very different system for recording numbers, a system that's much closer to the system that we use today. They had 9 symbols for the digits 1 through 9, and then they would combine these with special symbols for the powers of 10. So you had a symbol for 10, a symbol for 100, a symbol for 1,000, and so on, and you put these together. So if you wanted to represent a number like 327, you'd write the digit 3, the 100 symbol, the digit 2, the 10 symbol, and then the digit 7. It was not yet a full place value system in our modern sense, and one of the problems was that at this point, the Indian mathematicians did not have the digit 0. They did not have this placeholder, which enables us to tell the difference between 307 and 37, and so they used symbols for the power of 10 that was being recorded. This system, as we'll see in the next lecture, was also used by Chinese mathematicians. And one of the interesting questions out there is whether this system was originally created in India and then imported into China, or originally created in China and then imported into India, or perhaps created someplace else, such as Central Asia, and then imported into both of those countries, or maybe it just happened to come up independently. It was an idea that made good sense in both India and China. But at roughly the same time, we see a very similar system of writing the numbers. 0 itself would be invented sometime, well, nobody's really sure, sometime between 300 and about 600-700 AD. The earliest actual recording that we have of 0 being used as a placeholder in a number is actually in a Hindu temple in Cambodia that was constructed in the year 683 AD, and the year as recorded in the Hindu system was a number that actually used the digit 0. 0 had been used a bit earlier, not as a placeholder, but as a number that could be manipulated by the 7th century astronomer Brahmagupta. And this really is the first time that we have record of somebody working with a symbol that represents nothing, a symbol 40. 0 now enters the numerical system. And Brahmagupta did explain what happens when you add a 0 to a number or subtract 0 from a number, or what happens if you multiply a number by 0, you still get 0. And he wrestled a bit with this whole issue of what happens when you divide a number by 0, and essentially sort of left that up in the air, what happens when you try to divide by 0. In today's lecture, I'm going to focus on 3 great Indian astronomers. Again, these were men who were best known for their contributions to astronomy, but they also did a great deal of work in mathematics generally, in algebra, in number theory, and other areas of mathematics. These are Aryabhata, born about 476, died sometime in the middle of the 6th century AD. Brahmagupta, that I have already mentioned, who lived in the 6th century. And then Bhaskara Acharya. Acharya is an honorific title. It means scholar, so this is really Bhaskara the scholar, who lived in the middle of the 12th century. As I said in the last lecture, the astronomical works that were developed in Alexandria and elsewhere in the Eastern Mediterranean would be taken up by the Indian astronomers, and this appears to have happened in the first several centuries AD, under the Kushan Empire. Now, the Kushan Empire was an empire that had come down out of Central Asia to take over northern India, and it had strong connections with an older Hellenistic empire, the Seleucids, who were based in Persia and also in Central Asia. And largely because of this, the Kushan Empire maintained strong connections with the Eastern Mediterranean. And we do know that they brought astronomical texts from Alexandria and elsewhere. Strangely, it seems that they never actually imported Ptolemy's Almagest. That appears to be one of the books that was not translated into Sanskrit. But many of the other astronomical works of that same period were brought into India and were translated into the Sanskrit. And fairly soon after receiving the Greek texts, the Indian astronomers began to build on those and further develop their idea of trigonometry. The first of the great Indian astronomical texts is the Surya Siddhanta. We don't know exactly when it was written, probably in the 4th or 5th century AD. It's possible it was written even earlier than that. But already here in this first Indian astronomical work that uses trigonometry, we see that the Greek chord has been replaced by the half chord, what would come in the West eventually to be called the sine. And there actually is an interesting story behind how we got this word sine. The Indian astronomers quite naturally called it a half chord. The word for chord is jia, and half is ardha, so this was an ardha jia, a half chord. Although eventually they dropped the adjective half, they just referred to it as a jia or jiva. And this meant, though, the half chord. And from jiva, the word was taken up by the Islamic astronomers, and they pronounced it as jiba. And they wrote it in Arabic, which only uses consonants, as JB. And when the first Western astronomers were trying to figure out what this function was that was being described, they looked at these Arabic letters, JB, which of course did not represent any word in Arabic. Jiba is not an Arabic word, it's simply a transliteration of the Sanskrit word for this half chord. They looked at those letters JB, and the one Arabic word that they knew that used the letters JB was jaib, which means breast. And so they assumed that this was to be called a breast. Now, it's not quite clear how this happened, but perhaps out of excessive modesty, rather than calling it a breast, they decided to refer to the fold of a cloth that might cover a breast. And the fold of a cloth could be referred to as a sinus. And so this became a sinus in Latin, which in English eventually would become our sine. So we get sine out of a mistranslation of a transliteration of a Sanskrit word. The Indian astronomers also studied the cosine, which was the cotijia. And if you think about the bow and arrow, so we've got the arc of the bow, we've got the chord, and we've got the arrow. The shaft of the arrow, so that's the distance from the center of the circle to the chord, that is the cosine, or the cotijia. And the Indian astronomers also made great use of the ukramajya, and that's the tip of the arrow. That's the little part of the arrow between the chord and the arc of the bow. This would come to be called in English the versed sign. We no longer work with the versed sign. The versed sign, after all, is just the radius minus the cosine, so there's no real need to come up with a separate term for this. But if you look in the 17th century, something like Newton's Principia, his mathematical principles of natural philosophy, he does a lot with the versed sign, and this is where it's coming from. It's an Indian invention, and it comes out of describing that arc, that tip of the arrow. I'd like to spend some time now looking at the trigonometric tables that people came up with, and particularly the work of Aryabhata. Aryabhata, as I said, was born 476. He was in the Gupta Empire. The Gupta Empire had begun around 320, would last until about 600 AD. Aryabhata lived in Kusumapura, which was the center for astronomical work, very near the capital of Pataliputra, which today is modern Putna in India. He also was working with a circle of radius 3,438. And he almost certainly was not aware of Ptolemy's Almagest because, as I said, Ptolemy's Almagest was actually able to look at chord lengths for arcs all the way down to half a degree. And Aryabhata was working with chord lengths of 3 degrees 45 minutes. In other words, what he was doing was starting with a chord length for 60 degrees, and then from that you can get the chord length for 30, 15, 7.5, and then 3 3/4 just by taking half angles. So he had a much rougher table. But he did something that was extremely important. He was looking at the problem of interpolation. If you've got a table of values and you want to find some intermediate value, how do you go about doing that? Well, a natural way of doing this interpolation is that if you've got a value, say that's halfway between the two given values, you just take the output that's halfway between the two outputs. And rather than looking at the actual trigonometric table that Aryabhata was looking at, I'm going to show you a somewhat simplified table that illustrates the point of what Aryabhata and the later Indian astronomers were able to do. So what I'm going to do, on one side, I've got inputs that are the digits 1, 2, 3, and 4. And then I've got outputs that are the digits 1, 3, 7, and 13. And the question then is, if I've got an input of 2.5, what should be my output? Well, 2.5 is halfway between 2 and 3, so that suggests that my output should be halfway between 3 and 7. And so we might take 5 as the logical output. And that's what's called a linear interpolation. We're just assuming that things work as if they're on a straight line. But in fact, if you look at these output values, 1, 3, 7, 13, you see that the output values are increasing. 1 to 3 is a difference of 2, 3 to 7 is a difference of 4, 7 to 13 is a difference of 6. These differences are themselves increasing. Aryabhata did not just look at the differences, he actually took a table of the second differences. And he used that to refine the way in which he was going to do this interpolation. What is happening in this table is that as we move further down the table, the increase gets bigger. And so the increase in the output going from 2 to 2.5 should not be as big as the increase in output as we go from 2.5 down to 3. We need a bigger increase in output. Now, the total increase in output from 2 to 3 has got to be 4. So the output increases from an output of 3 to an output of 7. But how do we then arrange this output in order to take into account the fact that the outputs are increasing at an increasing rate? And one of the things that you can do is to decide that from 1 to 1.5, we've got to have a certain increase in the output. From 1.5 to 2, we've got to have a greater increase in the output. And the increase in the output has to increase by the same amount each time. And so we can do this if from 1 to 1.5, we have an increase of 3/4. From 1.5 to 2, we have an increase of 5/4. From 2 to 2.5, we have an increase of 7/4. And then from 2.5 to 3, we have an increase of 9/4. Now our increases are going up by the same amount each time. 7/4 plus 9/4 gives us our 16/4. Our total increase of 4 as we go from 2 to 3. And so that says that a better output for an input of 2.5 is 3 plus an increase of 7/4. So that gives us 4 3/4 as the desired output. And what is happening here is that you are beginning to get the idea of taking this table of values and doing what today is called a quadratic interpolation. So you're no longer using just a straight line to figure out what number should come out. You're using a much more sophisticated kind of technique for interpolation. And this idea of using a quadratic interpolation would be more fully developed by Brahmagupta. And Brahmagupta would actually show how to do an arbitrary quadratic interpolation for any kind of function that you might put in. So if you know the value of first differences and you know the values of the second differences, you can then use those in order to get a better idea of what the intermediate values in your table should be. Brahmagupta is an extremely important mathematician and astronomer. He taught at the great astronomical center of Ujjain, which is located on the western edge of Madhya Pradesh, near modern Rajasthan. Ujjain was founded around the 4th century BC, and it would exist until the 12th century AD. It would be an important mathematical center, and it would be so important as an astronomical center that it would mark 0 longitude, or what was the first meridian for Indian astronomers. Now, the first meridian in our modern world is the line of Greenwich, and that's chosen because of the Royal Astronomical Observatory in Greenwich. It's decided that that is 0 longitude, and you measure the longitudes east and west from Greenwich. In ancient Indian astronomy, that 0 mark of longitude was located going right through the center of Ujjain, the great astronomical center. As I mentioned before, Brahmagupta is the first person known to have used 0. He also is one of the first people known to have used negative numbers. Now, we will see in China that negative numbers came in much earlier, but only as intermediate steps. And Brahmagupta realized that you needed to be able to actually work with negative numbers and accept negative numbers as possible solutions. And so far as we know, he's the first person actually to accept negative numbers as solutions to mathematical problems. This interpolation formula, this quadratic interpolation, is often attributed to Newton, who would then go on and extend this to interpolation by polynomials of higher degree, cubic polynomials, 4th degree polynomials, and so on. Eventually, the Indian astronomers would realize how to do this, how to not just take first differences and second differences, but to work with third differences, fourth differences. as many as you needed in order to get a very accurate interpolation of the values. Brahmagupta also did work on Diophantine equations. So these are equations that were studied by Diophantus. And one of the examples of these that I gave earlier is the problem of Pythagorean triples. So 3, 4, 5, 3 squared plus 4 squared equals 5 squared. The kind of Diophantine equations that Brahmagupta studied, equations where we're only interested in integer solutions, are things like x squared minus 8y squared equals 1. If you find two integers that solve this, then the ratio of those integers gives you a very good approximation to the square root of 8, a good rational approximation. And he found a number of solutions to this. We don't know exactly the method that he used. All we know are the answers that he found. But for example, he showed that 3 squared minus 8 times 1 squared is equal to 1. And 17 squared minus 8 times 6 squared is equal to 1. And 3,363 squared minus 8 times 1,189 squared is equal to 1. Another one of the examples of the Diophantine equations that Brahmagupta studied are something squared minus 61 times something else squared is equal to 1. And here the answer gets much more complicated. One of the answers that Brahmagupta actually came up with to this is you take 1,766,319,049, you square it, you subtract 61 times 226,153,980. This quantity gets squared, and then that difference is actually equal to 1. This idea would further be developed by the last of the great Indian astronomers that I want to talk about, Bhaskara Acharya, born in 1114, died in 1185. He also was interested in this problem of finding polynomials that interpolate values in these tables of sines and cosines and versed signs. And he came up with something that would really anticipate developments in Western Europe that would come many, many hundreds of years later. And that is, in order to find a good polynomial to approximate the sine, he considered the rate at which the sine function is changing. What Bhaskara actually was looking at is the derivative of the sine function. And what he realized is that the rate at which the sine function changes is given by the cosine function. And the rate at which the cosine function changes is given by the negative of the sine function. And he saw how to use this fact in order to find what today we would call a Taylor polynomial, a quadratic polynomial that does a very good approximation to the sine function, very close to any value that you happen to know the exact value of the sine function for. So if you know the exact value of the sine, you know the exact value of the cosine, you can work out this quadratic approximation. And this really marks a new episode in the understanding of polynomials. Because up until now, polynomials had been thought of simply as things that are useful for solving problems that involve areas, then you use a quadratic polynomial, or problems involving volumes, then you're going to use a cubic polynomial. But now suddenly polynomials were being used for interpolation. They're being used to approximate the missing values in a table. And once you start doing that, there's no reason to stop at polynomials of degree 3. There's no reason to stop with volumes. The Greeks stopped with polynomials of degree 3 because it made no sense to talk about a 4-dimensional region. But if you're simply looking at the interpolation, suddenly it makes sense to go beyond degree 3 and consider a polynomial of degree 4, a polynomial of degree 5, a polynomial of degree 6. And we're not entirely sure where these different polynomials came from, but it seems that this was one of the important sources of the development of the idea of a polynomial of general degree. Also, the Diophantine equation that was studied by Brahmagupta, this general problem, you've got a perfect square, and you subtract some integer times another perfect square. I gave the examples where it's a perfect square minus 8 times another perfect square equals 1, or a perfect square minus 61 times another perfect square is equal to 1. That is known today as Pell's equation. And this is an equation that was not just studied by Bhaskara. Bhaskara actually was able to find a way of coming up with a solution to Pell's equation no matter what multiplier you were using. So you could use an 8, you could use a 61, you could use any number as long as it's not a perfect square. So you could take x squared minus 57y squared equals 1, or x squared minus 327y squared equals 1. And Bhaskara laid out a procedure that would enable you to find a pair of integers that would then satisfy that equation. Indian mathematics would continue after the fall of Ujjain. Ujjain disappears in 1235. This is when the Delhi Caliphate conquers Ujjain. The astronomical center is destroyed. At that time, at the time of the conquest, the astronomers in Ujjain are dispersed. Northern India ceases to be a center of important mathematical work, but the mathematical work of that time does move down into southern India, specifically southwestern India in Kerala. And we do have a series of important Indian astronomers doing work in mathematics down in Kerala, beginning with Madhava in the 14th into the early 15th century, Parameshvara, late 14th century into the 15th century, Nilakantha, 15th into the early 16th century. And what these astronomer mathematicians were able to do is to take the general idea that Bhaskara had done of taking a trigonometric function, looking at its rate of change, and using the rate of change, and the rate of change of the rate of change, and the rate of change of the rate of change of the rate of change, to come up first, as Bhaskara did, with a quadratic polynomial that's a good approximation to the sine function, and then a cubic polynomial, and then a fourth-degree polynomial. And eventually they saw how to get a polynomial of arbitrary degree. So you can get a polynomial of as high degree as you want. The higher you take the degree, the closer the approximation is going to be. And it's not clear which of these astronomers actually was responsible for it. It's generally believed that this goes back all the way to Madhava. But at this time, what they did was not just figure out how to get polynomials of arbitrarily large degree, they then made the jump to a polynomial of infinite degree, what today we would call a power series. So this is an infinite collection of powers of your unknown, which can be brought as close as you wish to the actual value of the function. So it's a representation of the function as a sum of powers of the unknown. The powers go out toward infinity. You can get as close to the value as you want just by going far enough out. This is work that was probably done in the 14th century. This is work that would not be redone in Europe until the very end of the 17th century. Unfortunately, the work that was done in India was lost to the rest of the world. The astronomers who were working on power series in South India were not able to communicate their results to anyone else. And the fact is that their way of approximating the sine was almost too accurate. The problem was that you can only measure the difference between two lights in the sky to within maybe a couple minutes of arc. So being able to calculate values of the sine or the cosine or the tangent to this kind of accuracy was far more than what was needed. And at this point, nobody could figure out any other uses for the sine or the cosine. The only uses for these trigonometric functions at this time was in astronomy. And since no one could figure out these uses, eventually knowledge of these power series would be lost. And it was only in the 19th century Actually, when British archaeologists managed to come across some of these old documents from several hundred years earlier, mathematicians then looking at them realized what actually had been accomplished. But it points out the importance of not just pulling ideas from the world around you. The ideas that you pull out of the world around you have got to be applicable to worthwhile problems in understanding the world. And once the mathematics becomes divorced from what is really needed, there is the danger that it's going to degenerate. In the next lecture, I'm going to move north from India into China, and we will see what was happening at this same time, the first millennium AD, roughly up to about 1300 AD in China.